In this video, we will try to solve a problem from torsion. But it's an interesting problem because we will, in a way, define the stiffness um, of a spring using the concepts of torsion. So let's see what I mean by this. So now, in this picture, you are seeing a spring which is generally called a closed coil. So let's write closed coiled helical spring. Okay, so the meaning of closed coil is this angle which this spring helix is making with horizontal, that is very small. So almost you can consider them to be horizontal. Okay, so these distances are not too much between coil to coil, and this is made up of a material whose shear modulus is G. The mean diameter of the helical spring is capital D, and the wire from which the spring has been made, so its diameter is small d. And now this picture is showing the view of the spring as if we are looking from below. Okay, so what it means is so this point where this weight W is attached is actually here. So the wires are twisted like that in circle, and at the end it goes to the center like this, and from here the weight is applied. And in the same way, on the other side, the wire is bent to the center, and at the center it is attached to the ceiling. So that's the meaning of this picture. This is from the bottom view of the picture. Okay, and this is the side. So now I can show the diameter maybe here. So this is the mean diameter actually. So that. So this is diameter D, and this is the wire diameter small d. Okay, and there are number of coils N. Okay, so here in this picture, N is 3. There are 3 coils. Okay. And then we are trying to find out the stiffness constant, the K, which is that how much force we apply for a spring to deflect by unit length. Okay, force per unit deflection, right? So force per unit deflection. So that stiffness in terms of these constants we want to figure out. Okay, for that, what we need to do is we have to recognize that this is a problem of can be approximated as a pure torsion. Why so? So now look at this end. Okay, so this end can be thought of as, I'm just drawing the end portion. So it's like the wire has come like that. Um, so this is the full wire, and then it has been bent like that. This point, and the weight is applied, or the force is applied in this direction, right? Now, so think about the cross section which is at this point. Okay, so this is the helical portion. So here also it's like a circle. So basically these are circles everywhere. Now at this, if you consider this portion, so this weight W which is getting applied, now From here to here, the distance is d over 2. So as if on this point, a torque of weight times d over 2 is getting applied, and that same torque gets transmitted across the complete length of the spring. So it is equivalent to, if you open this spring, okay, so the full length will become so the full length is something like this, and at this end the torque, so this is like, the torque, so that torque of W into T by 2 is attached or applied, and on this side, okay, it's fixed, and this full thing is rotated. So instead of keeping this in a lengthwise manner where it would have taken a long distance, now we have just made it into helix, okay, so that the stiffness actually is coming from the torsional stiffness, and that is converted into this linear translational stiffness, okay. So then let's see what we can do now with this. So the torque is known to be this. If this is the torque, then what will be the angle of twist that can happen here? So we know that that T over phi is nothing but Gj over L. So this length L is the total length of the spring, and this L then is nothing but pi d times, so this is the length of a single coil, right? So this is the length of a single coil times n, right? So this is the total length which we are considering. G anyway is the shear modulus, and now J is the polar moment of inertia of this cross section, okay. So that means J is nothing but pi d raised to 4 by 32, fine. So this is the J. Now, so from here, what we can do is we can calculate the angle phi. Phi will be say T times L over G times J. But then, okay, let's substitute everything here. Instead of T, we can now write W d over 2. L is say pi dn, then G is like that, and then this is pi d raised to 4 over 32. Okay, so that is the value of phi. Now imagine if that phi is the angle of twist at this point. So that means at this junction, this circle is getting twisted by angle of phi. If that gets twisted by an angle of phi, so then and then the effect is coming because every section has rotated by some amount, right? So this portion has rotated by some amount, this portion has rotated, and the end you are getting a rotation of phi as a cumulative sum of all those rotations, and then this phi times this r would be the deflection, right? So r means this d over 2, so that is your displacement, right? So that means we will say if the linear displacement is x, which will be nothing but the phi which we have got times d over 2, right? So then that will be written as, so from here we can put the expression with d over 2. So w d over 2 pi dn over g pi d raised to 4 by 32. That's the thing, and d over 2. Fine. And this is x. And how did we define our stiffness constant k? That was nothing but the weight which we applied divided by x, right? So this is the weight which we are talking about, and this is the x. So the ratio between these two is what we call as the linear stiffness of a spring, and that would come out to be equal to, if you simplify this, you will get this to 4 divided by 8 d cubed. So this is what is the stiffness in terms of the material property, the wire diameter, the coil diameter, and the number of coils. So you can see here, if you increase the wire diameter, that stiffness increases. If you increase the coil diameter, the stiffness decreases. And if you increase the number of turns, that in a way you can think um, that almost proportional to the length of the spring, so that is inversely proportional to the stiffness. So this is what we generally use, and this is what is the behind the scene what's happening. Okay, so it's a material plus geometry, both are contributing towards the linear stiffness of the spring. So that was a nice problem on torsion, and we will see another problem in the next video. Thank you.